Hi everyone, it's time to go through the week 8 notes. We've got indices and we've got scientific notation. So starting with this arithmetic of indices. Well, indices are powers. You might hear them called exponents, powers, to the power of, to the order of. There's all different words we use for it. But okay, indices are powers. We've got the base 2, so here's my base number. It's the large full-size number. And the index, or the power, is saying what it's being raised to. Okay. So we've got some terminology there, base and power. Now what that means, 2 cubed, I like to think of it as, tells me to write down 2 3 times. So 2 cubed to me, the main fault is to think, well, is it 2 times 3? Well no, we'll write 2 times 3 for that. 2 cubed is 2 by 2 by 2. So to me I think it's writing down 2 3 times and times them all. 2 by 2 is 4, by 2 is 8. Hence 2 to the 4 would be 2 by 2 by 2 by 2. And again, we'll see up to here would get 8, and it's by 2, so it's going to be 16. So that's what these powers are, that's what these indices are. It's telling you how many times to multiply itself. We've definitely had 2 squared before, which is 2 by 2. And you can see down here the pattern I've got. But you can see that it's building up. 2 to the 1 still follows that pattern that I was saying, that it's like telling you how many times to write it down. 2 to the 1 is just 2. So sure enough, I just write down 2, and that's what it is. Now we've got a few more powers to look at, but in general that's what we're talking about. Now let's look at some laws. Now law 1 says that when you've got the same base, in this example it's x, but you've got different powers, if you multiply them, you'll come together with the same, adding the powers. Now the explanation of that, 2 cubed, I've got it written here. 2 cubed is 2 by 2 by 2, times 2 squared is 2 by 2. What have I really got here? 2 by 2 by 2 by 2 by 2. It's 2 to the 5, which is exactly what the law is telling us. Instead of writing it all out, just add the tops. So if someone asks me, and I don't want to write it out, what's 2 to the 7 times 2 to the 14? I'd say, well, it's 2 to the 21. I've got 21 2's lined up there, 7 there, 14 there, so it's 2 to the 21. Now, so there's law 1. Note that the base have to be the same. If someone asks me what is 2 squared times 3 to the 4, well, I'm not saying I can't do it, I'm just saying I can't use this law to do it, because the bases must be the same, and here they're different. I could still answer this question, because 2 squared is a 4, and 3 by 3 by 3 by 3 gets me to 81. So I can do 4 times 81, what's that? 324. But I can't use this law. That is not law number 1. No, it's not. Okay, law number 2 is just, well, if when I'm timesing, I just add the tops, well, divide will be just subtract the tops. And that's exactly what happens. 2 to the 5 divided by 2 to the 3, they're the same base as 2 to the 5 minus 3. And 5 minus 3 is 2. And let's look at why it happened. Well, 2 to the 5 is 2 by 2 by 2 by 2 by 2. Divided by is the same as putting over. 2 cubed, there's 3 2's written down. I cancel 3 lots of 2's, and all I'm left with is 2 squared. That's exactly what happens. I subtracted 3 of them. So the 5 minus 3 became 2 squared. So again, if someone said, well, what's 7 to the 5 divided by 7 to the 10? Well, I'd say that's 7 to the 5 minus 10, which is a minus 5. They get trapped in writing 5, it's always left minus right, so 5 minus 10 does become a negative. We've yet to look at what it means, but it still follows the law. Okay, says law 2. Law 3 says a number raised to a power and raised to another power, all we have to do is multiply the powers. So 5 squared cubed is 5 to the 6. Exactly the same example here, just with 3. 3 squared cubed is 3 to the 2 by 3, which is 3 to the 6. Why? Because there's 3 squared and 3 squared and 3 squared. If I times 3 squared by 3 squared by 3 squared, well, that's 3 by 3 by 3 by 3 by 3 by 3. These 3 lots of 2 just makes up 6. So law 3 will always work. Again, if it's horrible numbers, 7 to the 12 cubed, well, okay, 12 by, that's 7 to the 36. So these examples, we don't do these write it out bit. This is just us explaining why it works. Law 4 says any base raised to a 0 index is always equal to 1. Well, okay, that's going to be true. X to the naught is 1, 7 to the naught is 1. Why? Well, I'll just get rid of this other scribble. If I follow this law, I'll do it in terms of numbers. Here it is in algebra. If I say what is 7 to the 3 divided by 7 to the 3, the index laws tell me 3 minus 3 is 0. The answer is 7 to the 0. 7 to 3 divided by 7 to the 3 is also, you know, what happens when I divide a number by itself? Well, I've got one of them up here or one of them down here. 7 cubed is what? 343. So it's like me asking what is 343 divided by 343? We can see the answer is 1. The exact same question, 7 cubed divided by 7 cubed, or 7 cubed over 7 cubed, gave me these two answers. 7 to the naught must equal 1. Anything to the naught must equal 1. Didn't matter whether I use 7 or x or 158. Anything to the power of naught is 1. So watch out for little traps. I might have it coming up. If someone said, what's 17 to the naught? I would say 1. If someone said, what's 2 plus pi plus 48 to the naught? Would say, oh, I don't care what's in there. All of this is raised to the naught. So the answer is 1. The trap question, what's 5 times 2 to the naught? I haven't put brackets around 5 times 2. So auto operations tells me to do the powers first. That's got to happen first. The 5 times can wait. The priority is 2 to the naught, and 2 to the naught is 1. So that's a 5 times 1, which is 5. So just because we're going to a new topic, well, auto operations is always going to be there, and we've got to obey it. So be careful of them. There'll be some in the exercises. Okay, negative indexes, or negative indices. We had one just then. Let's look at what it means. Now, hopefully it'll be a fairly logical thing. 2 cubed divided by 2 to the 5th. Okay, we know 2 cubed divided by 2 to the 5th is 2 to the minus 2. But I can also say 2 cubed over 2 to the 5th is 2 by 2 by 2 on top, and 2 by 2 by 2 by 2 by 2 on the bottom. So now if I go around cancelling some 2's, well, I've got a 2 there and a 2 there. I've got a 2 there and a 2 there and a 2 there and a 2 there. What have I got? The top is 1 by 1 by 1, and the bottom is 1 by 1 by 1 by 2 by 2, which is 2 squared. The only difference between the two answers is one says 2 to the minus 2, and one says 1 over 2 to the 2. That minus is the same as 1 over. Look at the answers. 2 to the minus 2. If I define minus powers meaning 1 over, that means the minus power means 1 over, and the 2 is still being squared. Whichever answer you look at, it's a quarter. And that's locked in. When you see a negative index, think 1 over. 5 to the minus 1 is a 1 over 5 to the 1. And we said before, 5 to the 1 was just writing down a 5, so it's a fifth. So, okay, just 1 over. What's 7 to the minus 1? It's 1 on 7. What's 7 to the minus 2? Well, the minus means 1 over, and the 2 still means squared, and 7 squared is 49. Okay, well if that's all negative powers means, is 1 over, okay, I can handle that. Now let's look at the next bit, where now it's saying that something raised to minus 1, a fraction raised to minus 1, turns it upside down. It sounds like something different, but it's not. 1 over and turning something upside down is the same thing. Let's look at that. I think the examples I've got here, or this one in particular, 2/3. Actually, I'll just do it at the moment to the minus 1. If someone says, what is 2/3 to the minus 1? I can say, well, that's 1 over 2/3. But that's a pretty messy way of writing things. You don't want fractions in fractions. So I might go back to my fraction topic and saying, well, 1 over 2/3 is the same as 1 divided by 2/3. We didn't do divisions in fractions, we did multiplications. We inverted and multiplied. We turned the divide into a times, and we took the reciprocal. In other words, we turned the fraction upside down. We left the first one alone. And what is 1 by 3 on 2? It's 3 on 2. What's the moral of this story? Raising a fraction to a minus 1, I can go all through the working, or I can just tell myself look, 1 divided by a fraction is 1 times its inverse, its reciprocal. So all I've got to do is flip it. Alright, well we can do that. I'll delete that again. And I'll say, okay, this question down here, it says 2/3 to the minus 3. Now, the minus means 1 over, which we just confirmed. 1 over just means flip it. Alright, I've used the minus. It's still got to get cubed. And now I could write this out manually like I've done here. 3 on 2 cubed means 3 on 2 times itself times itself. Or another little shortcut, if that's saying, these brackets are saying everything inside here gets cubed, because that's not equal to 3 on 2 cubed. If someone asks me what that is, clearly it's only the 3 getting cubed. The answer to that is 27 on 2. These aren't equal. These are saying, hey look, cube everything in these brackets, which means cube the 3 and cube the 2. Cubing 3 is 3 by 3 by 3. 3 3s are 9, 3 9s are 27. 2 cubed, well 2 by 2 is 4, by 2 is 8. There, this thing ended up just being 27 on 8. Or we could change it to a mixed fraction if we wanted. No one asked us to, but let's just practice. How many 8s can I get out of 27? Well, 3 8s is 24, with 3 left over, so that's 3 and 3 8s. Okay, so we've looked at a 0 index, we've looked at negative index with relation to fractions. What about, here's some more, fractional. What if the power is a fraction? Which initially, well, doesn't have to necessarily make common sense. Now, which example we go with first? This one's good, what I've written out here. I said 5 to the half times 5 to the half. I've pulled that out of nowhere, but we know that law 1 tells us, well, they're the same base, so you can just add the powers. And what's a half plus half? Well, it's 1. And what's 5 to the 1? It's 5. So I've said that 5 to the half times 5 to the half equals 5. Now, you may not be overly good on your roots. We haven't really dealt with them much. But really, the only thing that multiplies by itself to give 5 is root 5. Okay, the definition of root 5 is the number that times by itself to give 5. Got regrets on that example actually. It's correct, but I'm going to do one that might make more sense, because 9, the square root of 9 is going to be pretty. So this is a different question. What's 9 to the half times 9 to the half? Well, that's 9 to the half plus half, which is 9 to the 1, which is 9. We know what number times by itself to give 9. I'm ignoring the negative answer to this question. I'm just saying 3 by 3 will give 9. Hopefully you all agree with that. Hence that's equal. Those two things are equal. 9 to the half and 3 are the same thing. And what does times by itself to give 9? Root 9 does. By definition. Root 9 times root 9 gives 9. That's exactly what the root means. The square root sign says, what number times by itself to give me? Well, root 9 times by itself to give 9. Moral of this story, the power of a half means square root. Look at, if 9 to the half is equal to root 9, if 5 to the half is equal to root 5, a power of a half means square root. Okay, so that's another one. I know there's a bit of info coming into this one, but that's another law we've got. That, okay, power of a half means square root. Now, the analogy goes further, as I've written out here, that 8 to the third times 8 to the third times 8 to the third is 8 to the third plus third plus third, which is 1. And the definition of what number multiplies by itself 3 times to give 8, well, that's cube root. Okay, the cube root of a number is the same as a number to the third. So, again, just drill it down, David. What do we need to know? We need to know that if we've got an x to the half, where x is whatever, that's the same as square rooting something, the same number. X to the third means the cube root of x, which means what number times by itself, not just twice like here, what times by itself 3 times to give me. And it goes on. X to the quarter equals the fourth root of x. So say I said, what is 16 to the quarter? Well, we've got our calculators, so it's still doable, but we want to understand these indices. And there might be questions, say, without calculator, show what it means. We need to know that 16 to the quarter means it's the fourth root of 16. If we're being asked to do it without a calculator, it must be a nice number. Let's look at what powers of 4 might make it a 16. What's 1 to the 4? Well, that's 1 by 1 by 1 by 1. 1 to the 4 is just 1. Hence, the 4th root of 1 is just 1. What's 2 to the 4? Well, 2 by 2 is 4, by 2 is 8, by 2 is 16. Here it is. And hence, if 2 to the 4 is 16, the 4th root of 16 is 2. We've got a little thing going on here, like, times and divide, like plus and minus. To the power of 4 is the exact opposite to the 4th root. If I get 2 and raise the power of 4, I get 16. If I get 16 and 4th rooted, I'm back to 2. They're equal and opposite. 3 to the 4, well, that might rear its head. 3 by 3 is 9, by 3 is 27, by 3 is 81. If 3 to the 4 is 81, we might get asked, what's the 4th root of 81? And the answer will be 3. Okay, so if it's a non-calculator question, it'll be these sorts of numbers. If it's a calculator question, it doesn't matter. Okay, both of these I can do in the calc. I can do 16 and press my to the power of button, which normally is, I think it's like X to the box. Some calcs it's this little hat thing. And I can then put the power in as a quarter. And that'll answer me 2. Or we all should have an X root button. Something like that. Maybe there's a box in there. And if I want to find the 4th root of something, I just press 4, and then that button, and then the 16. So we've got 2 different ways to find the 4th root of something. Let's also, I'll underline that with another thing, Control A, delete, and say, alright, if you've got x to the power of 4, so if x has been raised to the power of 4, and I'm trying to claim that a 4th root will undo that, well, a 4th root is a quarter. What did law 3 tell us? It said when you've got a power to a power, you can just times them. What is 4 times a quarter? Well, it's like 4 and 1 times a quarter. That becomes 4 and 4. That is just 1. That's me just backing up my statement that to the power of 4 and to the power of quarter are equal and opposite. What if I do both of them? I'm just left with x. Okay. So now look at the next bit that says we can combine them. I just kept putting a 1 on the top. Really what I meant was, I said 16 to the 1 quarter is equal to, well, we're going to get to 2, but I said it's equal to the 4th root. That number there, yes, told us to make it a 4th root of 16. The 1 on the top still meant to the power of 1. I just ignored it, because I don't care about a power of 1. 16 to the 1 is still 16. So if the numerator is 1, I just went, whatever. What if the numerator was something else? What if it was 16 to the 3 quarters? Well, there's 2 things happening, as this little graphic down here shows. The denominator still tells me you've got a 4th root this. The numerator tells me it's still being raised to the power of 3. You could say, well, hang on, which should come first? The truth is it doesn't matter. I could say the 4th root of 16 and then cube it, or I could say the 4th root of 16 cubed. Again, being a calculator course, I don't really care what order I do it in. But if I was trying to do this without a calculator, do I want to calculate 16 by 16 by 16? No, the answer is no, I don't want to. But I can calculate the 4th root of 16, because I know the 4th root of 16 is 2. 2 by 2 by 2 by 2 is 16. So if the 4th root of 16 is 2, and all I've got to do is then cube that answer, 2 by 2 by 2 is 8. That was easy. That was easier than calculating 16 cubed. So, alright, so we're at the pointiest end. This is the worst sort of question. I can add one more thing, I will in a sec. But if you know that the power, the top, the numerator of any fractional power means to the power of, and the denominator means to the root of, then we're good. Let's look at this one. It said 8 to the 2/3. And I will always do the bottom one first, just because I'd rather deal with smaller numbers than bigger numbers. But I will repeat, I'll write it both ways. The way I do it is I'm going to cube root the 8 and then square the answer. But admittedly, I could have squared it and then cube root it. But this is my happy place, because the cube root of 8 is just 2. What times by itself 3 times to get 8? 2 does. And what's 2 squared? 4. It still would have worked in this spot. What's 8 squared? 8 eighths are 64. What's the cube root of 64? Well, what times by itself 3 times gives 64? It is 4. It's just harder. 4 by 4 is 16. 16 times 4 is 64. Still got there, but this makes a lot happier. Now, what if I inserted, how hard is it to change the colour on this thing? Not too hard. What if I inserted a minus here and made it the worst question we'll get? Well, what does minus mean? 1 over. Alright, I don't care. I can put a 1 over these things. I can put a 1 over that thing. I can put a 1 over this thing. If 8 to the 2/3 was 4, then 8 to the minus 2/3 will be will be 1 on 4. Actually, I should address that. It's easy to think that if your power is negative, your answer goes negative. Nothing to do with it. A negative power means 1 over. Doesn't turn things negative, it just means 1 over. We saw it before that it just meant there was more stuff on the bottom than on the top. But as long as if minus power means 1 over, then that's perfect. What if it was, say, 32 to the minus 3/5? Alright, trying to be nasty again. 32 to the minus 3/5. Well, my order of operations is the minus means 1 over, the 5 means 5th root, and the 3 means cube. Now, if this was a calculator question, that can go straight into the calculator. That'll spit out the answer. But if we're needing to show understanding or show all steps, what is the 5th root of 32? Well, it's got to be pretty. Okay? Otherwise, they wouldn't ask us. I know 1 to the power of 5 is still just 1. It's going to be 2. 2 to the power of 5. 2 squared is 4. Cubed is 8. 4th is 16. 5 is 32. The 5th root of 32 is just a 2. What is a 2 when I cube it? Well, 2 by 2 by 2 is 8. It's 1/8. 32 to the minus 3/5 is the number 1/8. 1 over the 5th root of 32 cubed. So I've really gone for the jugular there. But hopefully if you see that, if I got on the next page, page down, the overall summary. Now someone's knocking, but I don't want them to. So here we've got the summary of those rules, that like the worst case scenario, if you've got a minus it means 1 over, a 3 means to the power of, as in the numerator means power of, and the denominator means square root of. So there's a nice example there that we had 9 to the minus 3 on 2. The minus gave us the 1 over, but it was still 9 to the 3 on 2. The 2 on the bottom gave us square root, the 3 gave us cubed. The square root of 9 is a 3, so it became 1 on 3 cubed, which is 1 on 27. So there's like the worst case scenario of these ones, and hopefully you agree it's 3 things to note. Is it negative? What's the numerator? What's the denominator? Now, indices on the calculator, well, this is pretty particular to your calculator. Just some generalized instructions here that here's to say 2 cubed will be 2 to the power of 3. A lot of calculators will be 2 into the power of, is that key? 3. Either way, as long as you know your calculator, 2 to the power of 3, you can put it in there. Now, scientific notation. Interesting, I'll get rid of that. I'll get rid of that scribble. So, look at these numbers, a bit ridiculous. Here's a tiny number, the diurnal electron. Here's a massive number, the mass of the sun. You can see, in order to read that number, I'd have to, check what column it was in, I have to count all these zeros. So scientific notation is a much better way to say things. Now let's look at what this means. 4 by 10 to the minus 13 centimetres is the diurnal electron. That's saying it's 4 by 10 to the minus 13. We just saw what minus meant. It meant 1 over. We know that number 4 is a 4 and 1. So really what's happened here? We've said 4 times 1 on top, 1 times 10 to the 13 on the bottom. Well, that's 4 and 10 to the 13. That's 4 over a massive number. That's 1 with 13 zeros. Let's pretend I just did 13. So clearly that is one tiny, 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 tiny number, and that's a 4 in whatever relevant column, place value column, and there it is there. Now, they're over the top. We're not really going to deal with numbers that small or that big. Maybe in scientific notation, but we're not going to be forced to count through all the zeros. Let's do some more realistic ones. But first, let's define this form of scientific notation. Well, as you can see here, scientific notation is written in the form of A, where A is some number. Says here from 1 to, but not including 10. So maybe it's 5 times 10 to the something. Maybe it's 5 by 10 to the 6. Maybe it's 5.7 by 10 to the 6. So the number can be have lots of decimals. It might be 1.3887 by 10 to the 102. Okay, they're all scientific notation, but note what happens each case. There's only one non-zero to the left of that decimal point. That's why this statement is saying it's from 1 up to, but not including 10. So it could be 9.9 by 10 to the 7 maybe, okay? But I wouldn't write 10 by 10 to the 3. I'd write 1.0. So I've made that smaller, so I'm going to make that bigger. Those two, they're the same number. 10 by 10 to the 3, let's look at that. 10 by 10 to the 3 is a 10 with 3 zeros on it. 1 by 10 to the 4 is 1 times 10 to the 4, which is the one with 4 zeros on it. So they're the same number, but only this one is in proper scientific notation. 10 by 10 to the 3 is not. One non-zero to the left of the decimal point. So let's get rid of that stuff and look at the examples we've got. 1.2 by 10 to the 7, great. Only 1 to the left, 7 to the left, 2 to the left of the decimal point, 4 to the left, they're all good. But not 0.2, it's a non-zero to the left. What I would really do, if I had the number, it's still a number, it's just not scientific notation. If I want to convert 0.2 by 10 to the 5 into scientific notation, I'd have to times this number by 10 in order to write it as 2. You can write 2.0 if you want, just 2 will do me. 0.2 times 10 is 2. But if I'm going to times part of the number by 10, I better divide the other part by 10. I can't just walk up to a number and times it by 10, unless I want it 10 times bigger. But if I times part of it by 10 and divide the other part of it by 10, then I've evened out. And a 10 to the 5 divided by 10 is 1 less 10 on it, 10 to the 4. Think of it in terms of indices if you want. What's 10 to the 5 divided by 10 to the 1? Because I know 10 is a 10 to the 1. Do a subtraction of the indices, 5 minus 4. Okay, so scientific notation is still very indices based. Clearly we've got indices there. I want to prove that what I just did was true. 0.2 by 10 to the 5 is 0.2 with 5 moves bigger. 1, 2, 3, 4, 5. So it's really 20,000. What's 2 by 10 to the 4? It's a 2 with 4 zeros on the end, which is still 20,000. That is equivalent to that. Same number, but this one is in scientific notation. Okay, what else we got? Oops, did I just go too far? Page up, just checking. So we need to be able to convert from one to the other. Okay, first we're starting converting from scientific notation to basic numerals, as in to an ordinary number with no multiplication by 10 or anything. We started with, okay, that is I've gone over the top there. I'll just do a different one. Say I had the example 3.75 by 10 to the 4. Okay, well what's that mean? That means 3.75 by 10 by 10 by 10 by 10. That's what 10 to the 4 means. But I like to think of it as just as 4 moves bigger. Each time it got times by 10, the decimal point moved one spot. So if I had a 3.75, I'll just stick some zeros here. 1, 2, 3, 4 moves bigger. That number was really 337,500. This one, this exaggerating one, 4.28 by 10 to the 11, well that means move the decimal point 11 times bigger. That's why I went all the way back to here. Huge number. What if it's got a negative power on it? It just means go the other way. If I had 7.83 by 10 to the minus 2, it still means 2 moves, but it's 2 moves smaller, because really that's 1/100th. This thing is getting divided by 100, not times by 100. So 2 moves smaller Let's write it here. I know I've got to go to the left. Let's put some zeros there. 2 moves smaller. There we go. It's 0.0783. This one was only 7.3 by 10 to the minus 4. 7.3 with 4 moves became 0.00073. So that's all we've got to do. It's karaoke. This is telling us, the power of 10 is telling us how many times to move the decimal point. A positive number is telling us that we move it to the right. In other words, it's a big number. And negative index is saying move it to the left, as in it's a small number. Okay, well, what about the other direction? Let's look at some examples down here. Express 243 with scientific notation. So I start with 243, but I know I want it in the form something times 10 to the something. And I know that something only has one decimal point to the left, one non-zero to the left of the decimal point. So the decimal point is currently here on the number 243. I need 2 moves to the left. Now, 2 moves to the left means I'm making this number 2 moves smaller. So in order to correct this, I need to make this 2 moves bigger. As in, would you agree that 10 squared means 10 by 10 means 100? What is 2.43 by 10 times 10? 2.43 times 10 is 243. Yes, they're the same number. So it's like before. What did I really do here? I divided by 100 to turn 243 into 2.43. What do I have to do to counteract that? I better times by 100 to counteract it. And 2.43 times 10 squared is the same number as 243. So the next one was, what's that? 1, 2, 3, 4, 5, 6, 7, 8. I know that I want to introduce the decimal point here. I know I've just made this number a lot smaller, so this 10 has to be a positive number. How many moves? 1, 2, 3, 4, 5, 6, 7. If I get that number and times it by 10 to the 7, I end up with what I started with. So there it is. And the last one there, I'll do it up here, 0.00456. Well, I know that I want the decimal point to be here. I want it to be 4.56 by 10 to the something. So if I'm going to call it 4.56, I've made this number a whole lot bigger. 1, 2, 3 moves bigger. So I better be telling this number to make it back smaller again if you want to get to there. Again, I've timesed by 1,000 to make it look like this. I better divide by 1,000 to make it look the same. And 10 to the minus 3 is 1 over 10 to the 3, which is 1 over 1,000, which is dividing by 1,000. So yeah, it's small karaoke. We're just counting from where the decimal point currently is to where we want it to be, and making sure that if it's 10 to the 7, I'm discussing a large number. If it's 10 to the minus 3, I'm discussing a small number. That's that. What else have we got with here? Done that. Okay, the only other thing is how to use the calculator with scientific notation. And again, I won't spend long on it because we all may have different calculators. But I know on the FX82AU that we've got the times 10 to the key. There's a key down the bottom middle that says that, which literally presses times 10 to the for me. So here to input 5.517 by 10 to the 12, I just input the 5.517, press this times 10 to the button, which means I've now input 5.517 times 10 to the, and then I type 12, and that's exactly it. Some calculators have an X key, which means exactly the same as times 10 to the. So yeah, and sometimes it's times 10 to the minus 6. Now it doesn't matter which minus you use here. There's the big minus that's with the minus, plus, times and divide. Or there's another key which is bracketed little minus. Yeah, that's how we put in the calculator. So you'll see in the exercises, well, we've got some basic indices stuff. We've got our positive indices, negative indices, fractional indices. We've got scientific notation, and we've got some ones about, where did I miss it? Yeah, putting scientific notation into the calculator just to check that. All right, that was that one. See you next week.